Good day, I am Sigrid Maestro and I am here to present my undergraduate thesis proposal entitled Corn Cob Powder as a Reinforcing Material to Polypropylene.
Natural fibers regain its prominence due to the increasing environmental concerns such as pollution and depletion of petroleum resources brought by the extensive use of synthetic materials. Its characteristics such as low density, low energy consumption, low cost, non-toxicity, recyclability, wide availability, and sustainability are the reasons why it received a lot of attention from researchers as an alternative to synthetic materials. Maize, also known as corn, which can be a source of natural fiber, is one of the most important crops in the Philippines. With its wide production in the country, corn husks, cobs, and stalks are usually considered as farm waste after harvest, which are either incinerated or left to rot in the field. But most of the time, farmers opt to burn corn wastes, giving rise to health and environmental hazards to humans. One of the measures taken to address such concerns is the utilization of corn residues as a reinforcing material in polymer composites. However, such methods are not well known in the Philippines, since the corn crop waste management in the country lean towards bioenergy and biofuel. The objective of this study is to determine the effectiveness of utilizing corn cob as reinforcement to polypropylene. Specifically, it aims to observe the tensile strength, elongation at break, elastic modulus, flexural strength, flexural modulus, and impact strength of the resulting composite. Universal Testing Machine, or UTM, and EZOD Impact Test Machine will be utilized to perform the necessary mechanical tests. This study aims to present an alternative method which can be performed in the Philippines that would help in reducing the excessive amount of agricultural waste, providing extra source of income for the farmers, as well as reduce the use of synthetic fillers in composites. Corn cob powder would only be a reinforcing material and not a sole material in the fabrication of polypropylene composite. This study would focus on polypropylene only and not other polymers, as well as the mechanical properties of the fabricated corn cob powder and polypropylene composite. Corn cob is a lignocellulosic material. In the study of Garodimani et al. 2015, they fabricated hybrid polymer composites reinforced with corn cob particles and egg-glass fibers. In their research, they have determined the chemical composition of corn cob particles. According to them, corn cob particles are composed of ash content, which is 1.33%, lignin, that is 35.2%, cellulose, that is 41.5%, hemicellulose, that is 13%, and others, which is 8.97%. They also have concluded that the aforementioned hybrid composite can be an alternative to composite materials reinforced with synthetic fibers. Awad et al. In 2019 investigated the mechanical properties of a compression-molded polypropylene through three-point bending test, compression, and hardness. The mechanical testing performed are summarized under Table 1. Results show that polypropylene has good mechanical properties, and it could be attributed to the attachment of methyl on its polymer chain. An interesting application of corn cob and polypropylene was performed by Wan et al. In 2017, where the researchers investigated the mechanical, morphological, as well as thermal properties of corn cob flour, wood ash, and polypropylene composite. In this publication, maleic anhydride grafted polypropylene was used as a compatibilizer to improve the interaction between the fillers and the polypropylene. Results shown in the table clearly demonstrated the effects of varying amounts of corn cob flour and wood ash loads on the mechanical properties of composites. The conclusion could be drawn as following. First, the flexural modulus increases when the amount of wood ash is increased. This is an indication that wood ash serves as a physical cross-linking point which hinders the motion of polypropylene and higher stiffness of corn cob flour compared with polypropylene. The flexural strength decreased when corn cob flour was added into the composite. This could be attributed to the weak interaction and low compatibility between hydrophilic corn cob flour and hydrophobic polypropylene. However, when wood ash was added into the corn cob flour polypropylene composite, the flexural strength increased first and then decreased. This trend indicated that with loadings of 1 weight percent wood ash might have a good dispersion, but wood ash would aggregate with higher content, which gave rise to the poor dispersion of wood ash. Thus, the decrease of flexural strength. Third, the tensile modulus of the corn cob flour wood ash polypropylene composite increased with increasing the load of wood ash. But the incorporation of corn cob flour and wood ash into the composite resulted in the decrease of tensile strength. Fourth, the addition of corn cob flour and the loading of wood ash adversely affected the elongation at break of the sample. The composite with 10% weight wood ash possessed the minimum value of elongation at break, which is 8.6%. This consequence was in accordance with a rising stress concentration point, which might lead to the brittle behavior of the corn cob flour wood ash composite, polypropylene composite. Lastly, from notched eased impact strengths of the composites indicated that the addition of corn cob flour and the content of wood ash exhibited a negative correlation with the impact strengths of the composites. This was to be expected, because the additions of wood ash would disturb the continuity of polypropylene and act as a point of stress concentration, which would initiate microcracks. Another relevant study was conducted by Onuoha et al. 2017, where the group investigated the effect of recycled polypropylene composites loaded with corn cob powder on its mechanical properties. The findings on Figure 1 revealed that the tensile strength of the composites were found to be higher than that of the unmodified sample. However, excessive incorporation of filler may lead to filler agglomeration in the polymer matrix, leading to formation of microfiller due to the difficulties in achieving a homogeneous dispersion of fillers. The increase in flexural strength shown in Figure 2 could be attributed to the better rigidity and stiffness as a result of fair dispersion and distribution of the fillers in the polymer matrix, which efficiently hinders chain movement during the formation. For the yield strength in Figure 3, it could be observed that it increased progressively with increase in filler loading up to 20 weight percent, a behavior similar to that of tensile strength. The increased yield strength may be as a result of the strengthening effect of the filler due to the fair dispersion in the polymer matrix. For tensile modulus in Figure 4, generally, tensile modulus was found to increase with increase in filler loading up to 15 weight percent content and decreased with particle size. This could be attributed to the fair distribution of the filler in the matrix, which efficiently hinders chain movement during deformation. On the other hand, smaller particles enhance better dispersion within the matrix than larger particles. Hence, the decreased tensile modulus with increase in particle size. Lastly, Figure 5 shows lower elongations at break for the modified samples than for the unmodified samples. It is obvious from the data that elongation at break decreased with increase in filler loading and particle size. Filler incorporation into a polymer matrix increased the stiffness and hardness of the composite. This increase in hardness resulted in decrease in ductility of the material. Hence, as filler content increases, the ductility decreases, such decreasing elongation at break with filler loading. Further study was done by Salma et al. In 2014, wherein the researchers looked into the effect of corn cob content and maleic anhydride polypropylene as a compatibilizer to the tensile strength, elongation at break, and modulus of elasticity of uncompatibilized and compatibilized biocomposites from polypropylene and corn cob. The results from mechanical testing revealed that the tensile strength of the uncompatibilized biocomposites decreases as the corn cob load increases. This reaction could be attributed to the poor wetting of the corn cob by the thermoplastic matrix. Thus, a poor adhesion between the filler and polypropylene matrix arises. Similar trend has been observed for the elongation at break shown in the figure on the left for the uncompatibilized sample. This is due to a weaker interfacial region between filler and matrix. Lastly, the effect of filler loading on modulus of elasticity of the uncompatibilized polypropylene and corncob biocomposites is illustrated on the figure on the right. It can be seen that the modulus of elasticity increased with increase in corncob loading. An increase in the modulus of elasticity indicates the stiffness of the biocomposite samples. Overall, the compatibilized biocomposites have higher tensile strength and modulus of elasticity compared to the uncompatibilized biocomposites. The incorporation of compatibilizer proved to be effective in enhancing the compatibility of a system consisting of hydrophilic corncob filler and hydrophobic polypropylene. In the study of Ramos et al. In 2019, varying amounts of corncob which are 5, 10, 20, and 30 weight% were mixed to polypropylene. Through the universal testing machine, tensile and flexural tests were performed. It was found out that at 5 weight% corncob content, the tensile strength of the composite was about 27 megapascal, 26 megapascal at 10 weight% corncob content, and decreased steadily as the corncob content increased. Moreover, the obtained tensile strengths were lower in comparison with the neat processed polypropylene and unprocessed polypropylene, with values 30 plus or minus 6 and 31 plus or minus 6 megapascals, respectively. The elongation at break of the composites was also observed to decrease with addition of corncob. At 5 weight% filler content, the elongation at break value was found to be 7.2%, which decreased to 6.3% at 10 weight% filler content, and so on, still lower than the neat polypropylene. However, addition of corncob particles increased the elastic modulus of the composites, significantly at higher particle loading, around 10 up to 30 weight%, and was said to be caused by the stiffness of the woody ring that is similar to the composites made from wood and plastic. Different flexural properties were observed from composites with varying amounts of corncob content. The flexural modulus increased significantly from 1,259 megapascal for neat polypropylene to about 1,428 megapascal at polypropylene with 5 weight% corncob content, and continued to increase up to 1,814 megapascal for the composite with 30 weight% filler content. Its flexural strength, on the contrary, decreased as the corncob content increased. The impact strength of the composites is slightly lower than the neat polypropylene, and that the significant decrease was observed for corncob content of 30 weight%. The researchers were able to produce low-cost and lightweight materials by using corncobs. They have concluded that utilization of such byproducts in the fabrication of composites would reduce the use of polymers while providing good mechanical properties. Similar trend of elongation at break was observed in a study conducted by Ganawan et al. In 2021. Where corncobs were used as a reinforcing material in the polypropylene matrix. The researchers also utilized a universal testing machine to study the tensile strength and elongation at breaks of the composites. Their study has revealed that the elongation at break of the composites decreased with increased filler loading. Tensile strength, on the other hand, was found out to increase as filler loading increased. Contrary to the trend obtained by Ramos et al. 2019, where they have obtained decreasing values of tensile strength with addition of corncob particles. The researchers have stated that it is recommended to use corncob as filler in fabrication of polypropylene composites. Let us now proceed to the question and answer part. The first question is, based on your literature search, could the use of corncob enhance the mechanical properties of polypropylene, and to what extent? According to my research, utilization of corncob can enhance the mechanical properties of polypropylene. In the study conducted by Onuwawa et al. In 2017 and Gunawan et al. In 2021, their obtained results showed that addition of corncob filler in the polymer matrix improved the tensile strength of the resulting composite. And this may be attributed to the fair distribution of the filler, which hinders chain movement during deformation, as well as the strengthening effect of the filler into the matrix. Increase in elastic modulus was also observed in the studies by Salma et al. In 2014 and Ramos et al. In 2019. The increase in modulus of elasticity may be caused by the stiffness of the woody ring of the corncob. Hence, improvement in rigidity of the obtained corncob polypropylene composite. Lastly, flexural modulus was found to increase with the incorporation of corncob filler as mentioned by Juan et al. In 2017 and by Ramos et al. In 2019, which then again is associated to the stiffness of the corncob. For the next question, what could be the problems that you may encounter in using corncob as reinforcing material for polypropylene? The addition of fillers to polypropylene will usually improve its mechanical properties. But there will be some disadvantages because most fillers and reinforcements are polar. And polypropylene is nonpolar, resulting in weak filler polymer adhesion. And due to this incompatibility, problems such as poor dispersion, reinforcement, as well as poor mechanical properties could be expected from the final product, especially when there is an excessive particle filler loading. It can be seen in the studies of Ramos et al. In 2019 and by Salma et al. In 2014 that the tensile strength of the corncob polypropylene composites decreases with increasing filler loading. Ramos et al. Used SEM images to demonstrate poor chemical interactions between corncob particles and polypropylene macromolecular chains, proving that corncobs are heterogeneous particles scattered in a polypropylene matrix that can serve as stress concentrators. While Salma et al. Stated that the poor wetting of corncob by the thermoplastic matrix resulted in poor interfacial adhesion between the filler and the polymer matrix as the filler loading increased. Lastly, excessive incorporation of corncob particles may lead to filler agglomeration in the polymer matrix, thus resulting in poor dispersion, adhesion, reinforcement, and mechanical properties of resulting composite. In reference to the presented studies, it can be concluded that corncob powder is a feasible reinforcing material to polypropylene. Utilization of corncob residues can be a replacement to synthetic fillers in composites. That would be all for my presentation. Thank you.